Good morning. I'm Jeff Hammond with IGSHPA. Welcome to the July Dig Deeper webinar with Tom Wyer of Geo-Flo. We'll turn it over to Tom here shortly. I have just a few slides with updates on IGSHPA and some news that you'll want to hear about. So we'll get right into that, and then we will go to Tom's presentation. Just some news and updates to start off with. If you are interested in a Dig Deeper seminar like this one or our town halls, go to the events page at igshpa.org and you'll find that listing of Dig Deeper webinars and town halls. There's also a form to submit an abstract. So if you're interested in presenting at one of these webinars, be sure to fill out that form and we'll get you on the schedule. A couple of other news items here. Our business directory, that is going very, very well. We continue to add new business members, and that gives you an opportunity to be found by those who are looking for products and services. Our member portal is brand new as of June. If you haven't logged in, check that out. It's still in the same location on the IGSHPA website, but now you go to our new CRM software, and there are a lot more options on the member portal. That will continue to grow with more and more features. There's also an upgrade option if you have a number of individual memberships that you'd like to convert to a business membership. So lots going on with IGSHPA right now. Don't forget about the job board listings. If you have positions available, those can be placed on the IGSHPA website and give you a little bit more visibility for hiring individuals. Some interesting and exciting updates on the Department of Energy's Geothermal Technologies Office. They are looking for subject matter experts to review projects in the areas of design professionals, developers, community voice to get the word out, and workforce and labor development. This is part of that $13 million funding opportunity that was announced last week. And so if you're interested in this, just send an email to the info account at igshpa.org and we'll get you in touch with the right individuals. We're really excited about this new funding opportunity. A reminder on the annual conference in December. It's in Las Vegas, December the 6th through the 8th. We're partnering again with National Groundwater Association. This is their biggest show when it's in Vegas. So we're expecting a really, really good turnout. We already have a number of sponsors. We do have some left. The diamond sponsorship is still available, as well as a couple of gold, some silver and bronze sponsorships. So make sure you get that in as soon as possible so that you can become a sponsor of the conference. We do have speakers selected for the conference. We were fortunate to have 49 submissions. Thank you very much. And we will be following up with all of the speakers in the next couple of weeks. That website, the website will be updated with the conference agenda as soon as we finalize all of the information, and you'll be able to see who we have on target for the conference. Like the sponsorships, the exhibit space is filling up quickly. We have now filled all of the 20 by 20 booths, but we still have plenty of 10 by 10s, 10 by 20s. And I suppose that back wall, if you want a 10 by 50, we could make that happen as well. So check that out. The spaces are filling up quickly. Just a reminder, if you're looking for points and CEUs for the webinars, make sure that you send in the chat message to the IGSHPA account your name, and also please make sure you include your email address. That way Sally can count this as towards your CEUs if she has that information. So please send your name and email address if you're looking for CEUs for town halls and Dig Deepers. Just some housekeeping. I'll be monitoring the chat window, and at the end of Tom's presentation, I'll read off those questions, and we'll be able to address any questions that you may have. That maintains the presentation without interruption, and then we'll address those questions that don't get answered with follow-up emails. And one last item before I turn it over to Tom. We do have a disclaimer and a potential conflict of interest statement that we need to go through. The upcoming presentation represents the opinion of the presenter and does not represent any official position, opinion, or endorsement of any products or services by IGSHPA or its members. IGSHPA town halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It is the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. So with that, I'll ask Tom to share his screen, and let me do a quick introduction of Tom so you know who's presenting today. Tom Wyer is joining us, the president of Geo-Flo Corporation, which is the leading manufacturer of pumping systems, tools, and components for geothermal and hydronic systems. He has been working in the geothermal industry for 17 years, focusing on product development, applications, engineering, technical support, training, and sales. Tom is a volunteer on the IGSHPA and CSA technical committees and on the advisory board for the Design Technology Program at Ivy Tech Community College in Bloomington, Indiana, where he served as an assistant professor for 5.5 years prior to joining Geo-Flo. His formal education includes Bachelor and Master of Science degrees from mechanical engineering in mechanical engineering from Purdue University. So it's my pleasure to introduce Tom and take it from here. Thank you very much, Tom.
Thanks, Jeff. Appreciate that. Welcome, everybody. I appreciate you tuning in today for this deep dive into expansion tanks for geothermal systems. Oops. So this is the first time I've given this presentation. About 5 or so years ago, my colleague at the time, Jeff Hammond, and I wrote a white paper discussing geothermal expansion tanks and geothermal systems because we felt there was a need for really a broad overview and look at how we use expansion tanks and geothermal systems. So what I'm going to cover today is hopefully everything you would want to know about expansion tanks for use specifically in closed loop geothermal systems. I'm going to focus on diaphragm tanks. Also, you can consider bladder tanks as part of that category. I'm not going to talk about compression tanks that have an open air water interface. So I'm going to talk about how to size these things, how they work in a geothermal system, how do you figure out the size of these tanks, and where do you install them in a system. So pretty much everything that you could consider for expansion tanks. The last thing I want to do is also provide sources for you to investigate this topic for yourself. So in fact, the very first slide I put in here is the references that I've used in my research, both in creating the white paper itself and also in preparing for this presentation. So a lot of these will be very, very similar or familiar to you. Ashrae handbooks, the CSA IGSHPA standard 448, the Polyethylene Institute's, the Plastic Pipes Institute's excellent book on polyethylene pipe. If you're into any kind of hydronic heating, I would suggest Siegenthaler's book on modern hydronic heating. There's an excellent article that I'll reference in the presentation on understanding expansion tanks. It's an Ashrae publication from 2003, authored by Taylor. And again, I'm using some information that we wrote in our white paper, and I put a link in here in the presentation, so you can go back later on if you haven't read that paper and compare it to what I'm talking about today. Now, we created that paper many, many years ago, and as with anything else, when you continue learning and reading and doing further research, you look back at things that you may have done earlier in your career and say, gosh, if I could explain that a little bit differently, I'd change this word, I may exclude this sentence. But I think that if you take a look at the white paper and also pay attention to the presentation today and maybe go back and follow through the presentation on your own time, I think IGSHPA always makes these available for everyone offline after the presentation, and I can include a link on our website as well. If you compare that information, I think you'll get a pretty good overview of expansion tanks in geo. And finally, I reference calculators, and as Jeff mentioned, full disclosure, I do work for Geo-Flo Corporation. We produce these calculators and we manufacture some products for this industry, so that's full disclosure on that. However, you won't see during the presentation any product advertising. This is purely a technical presentation. You'll see that very shortly. So why do we use an expansion tank in geothermal systems in the first place? If you have been in this industry and done installations and service on expansion, service on geothermal systems, you'll know that the system pressure varies from season to season. In fact, it has the highest pressure in the winter and the lowest pressure in the summer, typically. The reason for that is that the HDPE pipe itself expands and contracts at a higher rate than the fluid itself. So as water warms, it expands, and as it cools, it contracts. And HDPE pipe does just the opposite. As it warms up, it expands. It doesn't do the opposite. It expands more quickly than the fluid itself, and it contracts more quickly than the fluid itself. So that creates a situation where we see these pressures varying over the seasons and having high pressure in the winter and the lowest in the summer. The other thing that we have to keep in mind is the HDPE pipe itself has viscoelastic and stress relaxation properties. So basically what viscoelastic means is that it functions kind of like taffy. So it has viscous properties and elastic properties. And like taffy, if you stretch it, it kind of pulls back a little bit, but it doesn't snap all the way back. That's the way HDPE pipe is. And stress relaxation basically means that the stress developed in the material degrades over time. So given enough time, the stress level approaches an equilibrium state. So those two properties of the pipe itself lead to a decrease in system pressure over time. So what that means is that you install a loop over a period of time, the pressure will tend to drop. And that can lead to some problems. And we've seen these problems in this industry over the years. Some of these problems include pump cavitation. If your pressure drops below the suction requirement of your pump in the system, it can lead to the pump to failing and the system to shut down, which means you're going to get a call back from the customer because their heat pump's not working. You can airlock the pump, which also leads to failure. And the thing to keep in mind about airlocking a pump is that little air bubbles that float around in your ground loop that are trapped in the system, either from startup, incomplete flushing, come out of solution during temperature changes, those kinds of things, or introduced during a maintenance procedure. Those small air bubbles actually become larger with decreasing system pressure. So as you're at a very high pressure, air bubbles in the loop cause no problems. They float around. You're not going to have much trouble with them. But as the system pressure drops and those air bubbles increase in size, then you can have some problems with your system. Noise, we've heard of homeowner complaints of systems that have noise in the piping. And you could also have low system pressure can also lead to negative system pressure, which means the pressure inside the pipe is lower than atmospheric pressure. When you have those conditions, you can actually suck air into the system because the pressure on the outside of the pipe is higher than the pressure on the inside of the pipe. So the pressure on the outside pushes its way into the pipe. So those are all problems that we have with low pressure in geosystems that we want to try to solve in some way. And one way of doing that is installing a diaphragm style expansion tank. So we could actually take a look at this concept of the pipe expanding more than the volume. And what I've done here is included some formulas. I'm not going to go through every single variable, but I want to point out a few things. One, we're assuming that the volumetric change of the pipe with these formulas, the pipe itself is unrestrained, which means that there's nothing holding the pipe in place. That leads to a conservative estimate of the linear expansion and the volumetric, the diameter expansion, the volumetric expansion of the pipe itself. Now, if you read into the Plastic Pipe Institute, what they say about the linear expansion of pipe, that the actual value is much less than theoretical value. And they suggest that field experience shows that it may be even up to half. But they indicate, as well as most engineers that you work with, you have to still design toward the unrestrained condition because that's the most conservative case. That's the most conservative estimate of the changing length, diameter, and therefore volume of the pipe. So you can use these formulas to figure out the increase in volume of the pipe. And you can compare that to the volumetric change in the fluid. This is one expression or one formula that you can use for finding the change of volume of a particular fluid. It gives you the values here. This is not the only formula, by the way, that you can use. This is just one version of it. Once we calculate the pipe volume change and the fluid volume change, we can compare those numbers. So I think the best way to do that is take a look at an example. And I picked this example because I'm looking at a surface water condition, or a lake loop or a pond loop with a heat exchanger in it. And this is what I chose. The reason I picked a pond loop or a lake loop is because it is very close to an unconstrained condition. There's not soil or rock holding the pipe in place. You could also think about a slinky mat on the bottom of a lake or a pond as being a condition where the pipe is fairly unrestrained. So I picked this example for that particular reason. So just very basic. We've got 3,600 feet of 3/4 inch pipe, and just 12 of these 300-foot spaced coils. We expect the temperature range from 40 to 90, and we're using water. So in this example, we can calculate the change in the length, how much that pipe is going to change. And 43,000 inches of pipe will change about 144 inches. And then we can calculate the diameter change of the pipe, crunch through all this stuff. We can figure out what the initial volume of my lake loop is in this case. It's about 110 gallons. And then we can calculate the change in the pipe itself. So this pipe will change in volume by 1.25 gallons over 110 gallons. So it's going to increase by 1.25 gallons in that temperature range. Okay, and the temperature range again was 40 degrees to 90 degrees. The fluid volume is going to change by 0.63 gallons. So this shows you that the pipe itself is expanding greater than the expansion of the fluid, which is exactly what we find in practice. So in practice, we know that happens. So therefore, the expansion tank should be sized to give back to the loop the difference between the expansion in the volume of the pipe and the expansion in the volume of the fluid. And if you do that, you can maintain system pressure. Okay, so really, I just picked this to illustrate that what we know sort of anecdotally, that the pipe expands more than the fluid and the system pressure drops. Wanted to put some numbers behind that for you to really take a look at it. So by looking at these calculations and with field experience, we know that we need some method of making up that pressure loss because there's a mismatch between the volume of the pipe and the volume of the fluid changes. So the current ANSI CSA IGSHPA 448 standard also makes mention of expansion tanks in systems. They recognize, the standard recognizes that in a pressurized system, you are going to have these pressure losses. You're going to have to maintain that system pressure so that you don't have problems with the circulator. You don't have problems, as I mentioned earlier, with air in the system or the system dropping below atmospheric pressure. So they suggest that you install an expansion tank. That's one way of doing it. You can also install a pressurization system, like a glycol feed system, or the provision number 3 was provided to allow for people to do what a lot of folks in the industry have done for years, which is pressurize the system to a really high value with your flush card at the beginning of installation and hope that that is enough to maintain that minimum static pressure over the course of the year. And it may not be the best provision, but it does allow you to keep doing what you have been doing. However, using an expansion tank will put you in a position where you don't have to concern yourself as much about figuring out what that minimum static pressure needs to be. So just wanted to point that out because the standard does suggest that we should do something like installing an expansion tank. I also wanted to look at, a lot of folks do hydronics that also do geo. So I wanted to take a look at the differences between expansion tanks in boiler systems or traditional hydronic systems and geothermal systems. So in a hydronic system, a boiler is hooked to some rigid piping like copper, and that piping expands and contracts very little over the operating range, but the fluid does. It still expands quite a bit, going from a cold temperature up to a hot temperature to condition the space. If you don't include an expansion tank, then that fluid's going to expand quite a bit faster than that rigid piping, causing really dangerous increases in pressure. You could have, something like a bomb in your basement. Boiler systems typically also include pressure relief valves to prevent those dangerous overpressurization conditions. We are not usually installing those in geothermal systems on earth loops. We don't usually include pressure relief valves. In a boiler system, you size the tank to prevent these system overpressurization conditions so things aren't dangerous. You have to make the tank big enough so that water doesn't come squirting out of the pressure relief valve. And you also want to make sure the tank is appropriately sized so that as the system pressure increases, that it stays below all of the rated components that are installed in that system. As I mentioned previously, the point of an expansion tank in a geosystem is typically to prevent low system pressure. The reason we're more concerned with low system pressure than overpressurization is that the properties of HDPE pipe that I mentioned earlier, the stress relaxation and the viscoelastic nature of the pipe itself, means that overpressurization typically isn't a problem, because if you have a situation where the pressure starts to climb, the pipe itself does stretch some. The stress relaxation helps drop the stress in the system, decreasing the system pressure. I have seen a couple of instances where the system pressures spike. So a couple of times in my career, I've had phone calls where people say, look, I've got this system installed, my pressure is spiking. It's going from, my installed pressure of, say, 30 or 40 PSI over 100. And in both of these cases, there were installations where there was some monitoring equipment that was installed on the system, looking at the system pressure, or some gauges installed so that the installer could monitor the pressure of the loop. And what we found out in those circumstances was that the pipe was in heating dominant locations with long run times. So some of the more modern geo equipment includes things like variable speed compressors that run a lot more hours. And there were vertical bores and had some level of fluid around the pipe. So the loops themselves had plenty of antifreeze. There wasn't any issue with antifreeze, but what we determined was that the fluid around the pipe actually froze, squeezing the HDPE pipe and driving the pressure up. So in that kind of a situation, an expansion tank could be used to control overpressurization, but that appears to be very, very rare. And I'd like to hear from some of you guys' comments on that a little bit later if you've seen that for yourselves. Okay, how does the expansion tank actually work in a geothermal system? Well, we know that the loop pressure is highest when the loop temperature is the coldest, which is in heating season, and lowest when it's the temperature in the loop is the highest. So what we see here in this little example is that in a bladder tank, when the loop is warm, all of the fluid is pushed into the loop, and as on a cold loop, as the fluid contracts, it is driven into the tank and increases the pressure on the inside of the tank. So the amount of water that this actually holds is something called the acceptance volume. We're going to talk a lot more about acceptance volume in the next few slides. Okay, so these figures give an example of a expansion tank installed, a schematic installed into a system. So again, what we're really concerned with, one of the considerations we have to take into account is the pre-side pressure. It's also called a pre-charge pressure. A lot of expansion tanks, in fact, most expansion tanks in the market have a valve that allow you to set the airside pressure or the pre-charge pressure of the tank. And that pre-charge pressure is typically when the bladder itself is extended fully inside of the tank, taking the shape of the tank. In a boiler system, that pre-charge is set at a cool temperature, so the tank actually starts to function as the fluid warms. So that's the way the pre-charge set is set for a boiler system. It's to allow the tank to start functioning at that pre-charge pressure. In a geothermal system, it's a little bit different. So if we look at this first picture, you've got a system pressure of 10 and a precharge of 12. There's no fluid that has been pushed into the tank or accepted into the tank. In the second figure, you can see that I'm driving the system pressure up, maybe with a flush cart or some other external means, from 10 psi to 20 psi. So now I've got I've forced some fluid into the tank. That compresses the air, and my air pressure is equal to my fluid pressure. In the next figure, you see that if I keep driving my tank up, my system pressure up, it's going to drive more fluid into the tank, creating a higher pressure. So the function of a tank in a geothermal system is quite a bit different than a boiler system, in that the precharge pressure is the pressure at which the tank actually stops working to prevent low pressure. So as you can see in this last figure, if my system pressure starts to drop for some reason, I've got a little leak in here, I've got a lot of expansion of my loop, and my tank is too small, this 12 psi of air pressure is going to force fluid back into my loop only down to 12 psi. And at that point, the pressure in the system is going to keep dropping, and the system will function as if this tank is not even installed. Of course, it will still allow for some overpressurization, which means it'll still absorb some fluid. But again, that's typically not what we're concerned with in a geothermal system. So the precharge itself should be set as low as you possibly can to get maximum capacity from the tank selected. It'll also allow you to choose the smallest tank for a particular system. So that understanding that precharge is quite important for that. So the precharge is directly related to the ability for the tank to actually absorb or accept fluid into it. So we saw in that last slide. And that acceptance volume is the amount of fluid that the tank can actually hold at any particular pressure. So I've got a chart here showing some different acceptance volume. It's how the acceptance volume, or the fluid that's pushed into the tank, changes as a function of tank size and of precharge. So this first blue line you see here, it's a very small tank. It's only a 3/4 gallon. It's got no precharge. And again, I'm assuming no elevation head that's going to force water into that tank at the point of installation. That tank with zero precharge, as the system is pressurized, is absorbing this amount of fluid. So if we pressurize our system to 50 psi, I've actually absorbed almost 0.6 gallons. And interestingly, if you compare that to this 2-gallon tank with a 30 psi precharge, it accepts the same amount of fluid. So this sort of shows you how that precharge affects how much fluid is accepted into or forced into the tank during commissioning or during setup of your system. You'll also notice in this chart that these guys never reach a flat line, right? They're always increasing, which means that the air, you can't compress the air to zero volume. So the acceptance volume for any tank is always less than the size of the tank itself. So a 2-gallon tank can never accept 2 gallons of water. It can get real close if you drive the pressure up high enough. As you can see, all of these curves start approaching a limit, but it can never accept the full volume of the tank size that you choose. So when we're setting a precharge amount, we should set that precharge to be as low as we possibly can. And really, you set it, the easiest way to think about it is you set it to match the water column or the elevation head at the tank's installation point. So if you have an expansion tank that's installed in the basement, for example, and you have 10 feet of piping above that, then you'd need to set your precharge to 10 feet. Otherwise, that 10 feet of head, that elevation head, will force some fluid into the tank, reducing its capacity slightly, okay? So you want to set that precharge to match the water column. Simple formula to figure that out: measure your piping above the installation point, divided by 2.31 feet of head per PSI, and that gives you your precharge. Now, most commercially available hydronic tanks have a precharge of 12 PSI, and you got to be really careful. And notice I've said hydronic and really put some emphasis on that, because There's a lot of tanks out there that have 30 PSI, 45 PSI pre-charge that really aren't intended to be used for hydronic systems. If you take a look at 12 PSI that's available in most hydronic tanks, and you just install that thing and you don't change the pre-charge, then it would look like this for a 2-gallon tank. It's not going to accept any fluid until you hit 12 PSI, and then it's going to start accepting fluid into the tank, which basically means that if you have 27 feet of pipe, about 28 feet of pipe above the expansion tank, then then there's not going to be any fluid forced into the tank until the water column exceeds that height. So you could have a couple of story building, in other words, with piping going up 2 floors in the expansion tank in the basement, and your pre-charge would be about the right value. So what happens if you don't change your pre-charge? You do lose a little bit of your tank's not going to absorb anything until you reach a certain value. And that's the point at which your tank's going to stop working. Okay. All right, we can really get really detailed about how do we calculate how much fluid is inside inside the tank. And I want to include this just for completion of the entire presentation. You can go back and look at this later to follow the math on this thing. But really, the fluid inside the tank can be calculated using Boyle's law, which basically says the pressure and volume are constant. So the pressure at a certain, on the air side, I should make that clear. Boyle's law has to do with the air side of the tank. So the initial pressure times the initial air volume is going to be equal to the second air pressure times its final air volume. So in other words, as the volume decreases, the pressure increases. That's all that this Boyle's law is trying to tell us. So that figuring out how much air we've got inside of that tank will also then tell us how much water we have as the system pressure is increased. And I've kind of done the math here for you on that. And what we come down to is that the amount of water, or the amount of accepted fluid volume, or the acceptance volume inside that tank, can be given by this formula. Okay, we can normalize this formula to make it work for any size tank just by dividing out the volume, the V1 term, which is the initial air volume. And the initial air volume, if the bladder is fully extended, is the volume of the tank. So in other words, if we take the volume of the tank and multiply that by this number, 1 minus the initial pre-charge value divided by the maximum system pressure, we can figure out how much fluid's in the tank. All right. And that's what we did to generate this curve. So these curves were generated using this function. You sometimes will see this value called acceptance factor in the literature. So if you come across that, what we're talking about is this term right here, 1 minus the initial tank pressure divided by the maximum tank pressure. So how do we size the tank? Well, we know a couple of things. One, if we start out with too small of an acceptance volume, then it's not going to be that helpful. So we saw in that chart that if the acceptance volume is not correct, which means I've either got too small of a tank or I've got the wrong pre-charge. So if I don't have enough acceptance volume, the tank is not going to do anything to help me prevent low system pressure. If you use a larger tank than you need, it's not going to cause problems. The only problems you're going to get into is that it's going to be a slightly higher installation cost, which shouldn't usually be that big of a deal because the tanks are relatively inexpensive compared to the system cost. And they require a little bit more mechanical room if you have a bigger tank. So there's a space consideration. Now, what you need to do when you're sizing expansion tanks is to figure out what your total acceptance volume is, and it needs to be greater than the expansion of the pipe over that expected temperature range. And I want to point out also that you can use 2 small tanks instead of 1 large one. That's perfectly acceptable. Just to reiterate the issue with boilers versus geo, acceptance volume in a boiler system has to be greater than the fluid expansion. Acceptance volume in the ground loop system has to be greater than the pipe expansion. So the tank size depends on the acceptance volume of the tank at the system pre-charge pressure. And that system pre-charge pressure is usually dictated by the deadhead pressure of your flush cart. So now we get into the nitty gritty. How do we actually use all the values that we have to figure out what tank size we need? Well, the Ashrae handbook does give us a guide, and we're going to dissect this a little bit. And if you've sized expansion tanks before, you've probably looked at the Ashrae formula. It's the one that's most probably well known. And a couple of things I want to point out on this. One, that the linear coefficient expansion on rigid piping like steel is about is a lot less than the expansion of HDPE. So it's by a factor of 10. So the expansion coefficient for something like steel piping is 6.6 times 10 to the negative 6, whereas HDPE is going to be somewhere like 67, maybe 100. And I've seen this value differ in different literature, so I did note that here on the slide, so that there is a range of values that's reported for linear coefficient of expansion. But we're going to look at this a little bit more. The reference 5 that I gave earlier, this gentleman Taylor proposed in the Ashrae article that he wrote, that we basically size an expansion tank so the acceptance volume is greater than the volume of the water as it expands, exactly as we talked about earlier. We sort of started setting the groundwork for that earlier in some of the earlier calculations. So he's proposing that we use this formula. Now, the one thing that Taylor does is a couple of things. One, he explicitly says that this volume, the pressures in the denominator are the initial pressure of the expansion tank, the pre-charge pressure, in other words, and the maximum system pressure that you're looking for, the maximum pressure that tank would see. That's a little bit different than the Ashrae formula. The Ashrae formula says that P1 is the pressure at the lower temperature, and P2 is the pressure at the higher temperature, which really leads to some interesting things if you're trying to use this formula for geo, because we know that at our lower temperature is when we have our higher pressure, okay? So that's something that's different from when comparing a boiler system or standard hydronic system to a geothermal system. So it's that relationship of when my pressure is the highest, right? We're going to investigate that more in a second. But Taylor basically says, hey, look, we're going to ignore this term. So if we look at this term in the formula is the relative expansion of the fluid. This term is the relative expansion of the piping. And this term is really the correction factor for the air as it gets pressed into the expansion tank. So Taylor proposes that we just ignore this term, okay? We just ignore this pipe expansion. And when you do so in a heating application, a standard boiler situation, it gives you a slightly larger tank size because you're not subtracting out the expansion of the pipe itself. Okay, I think the best way to take a look at this is to look at an example. So what we're going to do is take a look at a system that's got 100 gallons of fluid. It's using all HDPE piping. We want to keep a minimum static pressure of 12 on the system, and we're gonna pressurize this thing at the beginning with our flush cart up to 50 psi. We're going to go. We've designed the ground loop to have a minimum temperature of 35 and a maximum of 85. So we could take these numbers, plug them in to our Ashrae formula, and then take a look at the result. So this first term that we have here, this is the relative volume change in the fluid. So if I take the initial volume, which is V sub S, it's the initial 100 gallons of fluid, and multiply it by the ratio of the specific gravities of the fluid at the lower and higher temperatures, what I see is that the fluid's going to expand 0.44 gallons over that range, okay? If I look at the expansion of my pipe over that same temperature range, so that's my initial volume times this factor, I see that my pipe, once again, expands a lot more than my fluid, okay? So if I subtract those two values, this one from this one, I get negative 0.57 gallons. So that's kind of curious, all right? So that basically reinforces the fact that our pipe is expanding faster than the fluid. Now, interestingly, if we use the Ashrae formula as it specifies and says, okay, P1 is the pressure at our lower temperature. Okay, that's higher pressure at lower temperature. P2 is the lower pressure at the higher temperature, as we know happens in a ground loop system. We end up with a negative number as well. So we divide a negative number by a negative number, we get a positive number. So using the Ashrae formula that says that our tank size should be 0.4 gallons. Unfortunately, 0.4 gallons is for a tank size is less than the acceptance volume. Okay, it's less than we need, right? It's less than this negative 0.57. So this is a bit of a problem, right? This term should be used to increase the size of the tank over the relative difference between the fluid expansion and the pipe expansion. But when you use the Ashrae formula as dictated, it gives you an incorrect result. So what if we flip P1 and P2 like Taylor proposes? So instead of using the lower pressure temperature ratio that we have from the Ashrae formula, we flip those two numbers, okay? And when we do that, we get a 0.59, and we could then take our previous value of negative 5.7 divided by 0.59, but then we get a negative answer on our tank size. You can't have a negative tank size. So that creates some additional confusion. What do? Do we take the absolute value of this 0.97 and say that's the tank size we should use, or what? I mean, what do we do? Now, if we look at all the other stuff that I've presented so far in the presentation, it turns out that if you take a 1 gallon tank, you can't have a 0.97 gallon tank. And we'll just round that to 1 because you could probably buy commercially a 1 gallon tank. That will actually accept 0.59 gallons of fluid when it's pressurized to 50 psi with a 12 psi precharge. So as we saw earlier in the presentation, the fluid accepted into the tank, the acceptance volume of the tank is going to be the tank size times that acceptance factor, which, as it turns out, is Pi divided by P max, as Taylor proposed. And that gives us a positive 0.959 gallons. Okay, so this work indicates that what we should be doing, and it follows logic, that if we rearrange the Ashrae formula, then we can size our tank based on the minimum fluid pressure that we want in the system. So all we have to do is recognize that our expansion of our pipe is greater than the expansion of our fluid, subtract those two values, and divide that by the acceptance factor, or the amount of air side that you need inside your expansion tank to determine your tank volume. Okay. So what am I saying about Ashrae formula? It's been used a long time by engineers, so it definitely works. All right, it's valid for boiler systems and geosystems to prevent overpressurization, but you have to understand what the purpose of the Ashrae formula is. And I would suggest exercising caution when using the formula as printed for maintaining minimum loop pressures, particularly in loops that are unrestrained. Right? If you've used the Ashrae formula and you've had good results, it's because there's a lot of conservative measures built into that, because we are assuming unrestrained loops, unrestrained expansion of the and contraction of the piping. So if you've used it and it's worked, that's why. But if you dig into the numbers, you'll see that when you take an acceptance factor as it's printed from the Ashrae formula, it actually results in a smaller tank size than you would expect. Taylor's approach of ignoring the expansion tank, the pipe expansion, is more conservative for overpressurization, but again, it's not really applicable for underpressurization or expansion of HDPE pipe. So the correct approach is to compare the volumetric expansion of the HDPE pipe to the volumetric expansion of the fluid, and make sure you pick a big enough tank that will have enough capacity to maintain the desired loop pressures. There's a lot of ways you can get to that. So you can use that inverted, the rearranged Ashrae formula. You can use fundamental calculations like I showed you on slides 5 through 9, which just calculates expansion of the diameter, expansion of the length, therefore the expansion of the volume, then calculate the expansion of the fluid, compare the two, subtract them, figure out your tank size. So the calculator that we put together for sizing tanks for geothermal loops. It's available on our website, geoflo.com calculators, free, no charge. Sign up for an account, you have access to it. Uses this fundamental approach and is based on maintaining minimum loop pressures, not controlling the maximum pressures. Although I should say that even though this is the case, that I'm not interested in controlling the maximum pressure, if you're doing something like a commercial system and you have devices in the system that are included, such as a pressure makeup system, that you're actually maintaining a minimum pressure by using an external pressurization device, and you're really concerned about overpressurization, sizing the tank in this way, it leads to a conservative estimate as well. So if you use the expansion tank calculator, basically you can enter, if you already know your system volume, you can just say, I'm going to use a manually entering my volume and stick that in there. And there's a section down here that allows you to take a look at the percentage of HDP pipe versus the percentage of other pipe in the system. Or you can say, I want to look at the lengths of pipes because I don't really know what my volume is. I'm going to enter those enter the various lengths of the pipe into the tables and then come up with a solution. So what I've done is just put in a screenshot of the website, taking a look at what we would do with, from example one of 3,600 feet of 3/4 inch pipe. It's about 100 gallons, as we talked about earlier. Acceptance volume is 0.6. That's what I need. I need that minimum acceptance volume to be able to do that. And in order to get that acceptance volume, I'm going to need something like a 2-gallon tank, right? So if you pick up a commercially available 2-gallon tank, it's going to give you that acceptance volume when you go from 12 psi pre-charge up to 50. Now, if you change that pre-charge pressure, the expansion tank size that you choose may be smaller. Okay, so that pre-charge pressure does impact the size of the expansion tank that you select. There's one other area that you can enter some information to determine the acceptance volume over these two pressures for any size tank. So you could ignore everything above in the calculator if you wish, and say, look, I have a tank that is X number of gallons, maybe 50 gallons. What's the acceptance volume from a pre-charge of this up to my maximum static pressure desired? Okay, so that's how you size the tank. You can do it by hand. You can use these calculators that are available to you online. But I think the important part of that portion of the presentation was the concept of comparing the volume of expansion to of the fluid to the volume of expansion of the pipe. Now let's take a look at the installation locations. So you can install an expansion tank in a closed loop system in a lot of locations. And I would argue that it should always be installed on the suction side of the circulator. Some people say that that's the only place that you can install, and that's not the case. You can install an expansion tank in other locations in the loop, provided that you take into account installing it at those other locations. So there's some other considerations and calculations that you have to be made. I don't have time to go into those in this presentation, but reference 5, the article by Taylor, goes into those in very, very deep detail. So I'd suggest that you take a look at that if you're planning on putting an expansion tank either in a hydronic system or a geosystem at some location other than the suction side of the circulator. Okay, so we're going to look at a quick example. Let's say we have a system, ground loop, heat pump, circulator with no expansion tank. Basically, when my pump is off, everything's at static pressure. When my pump turns on, my circulator has to overcome the head loss in my piping. So I get pressure loss from the discharge side of my pump. It's going to lose pressure over to the heat pump. It's going to lose pressure through my coaxial heat exchanger, through the piping, through the ground loop, all the way back to the suction side of my circulator. So if you have no air in your loop and you didn't have to worry about your pipe relaxing over time, then this is quite a fine scenario. Now let's look at what would happen if we have an expansion tank installed in a couple of different locations. First, we'll take a look at it, install it on the discharge side of the pump. So if the pump is turned off, my circulator's off, and my valve is open, and I've got my system charged to 30 psi. I've got 30 psi on the air side. I've got 30 psi static throughout my loop, assuming no elevation changes. If I turn my pump on and have this isolation valve closed, the discharge pressure jumps up to 40. We saw that previously with no expansion tanks. We know when the pump turns on, the pressure in the pipe right at the discharge of the pump is going to increase. It's going to increase to match the head loss around the loop. Now, if that pump is on and we open that expansion tank, open the valve to the expansion tank, what happens? Well, a tiny bit of fluid will go into the expansion tank. And that pressure will increase inside the expansion tank. I've rounded to 30, but if you do the math, it'd be like 30.01 or something very, very small. So a little bit of fluid's going to go into the tank to equalize the pressure on the air side of the system side, and then you lose pressure all the way around. So now my suction pressure is only 20 psi instead of 30 psi. Again, in this case, not too big of a deal. But if you have a system installed, such as this, where you've got a fairly high head loss, I've got 46 feet ahead on this particular loop, and let's say I've got my system installed at 12 psi, expansion tank once again installed on the discharge side of my pump, turn the circulator on, I'm maintaining 12 here, and then I'm losing 20 feet ahead all the way around my pipe. So I end up with a negative suction pressure. Okay, so that means that my pressure inside my pipe is less than atmospheric, which can cause the problems that I suggested earlier about sucking air into the system or collapsed hoses, cavitating the pump, etc. If you move that expansion tank to the suction side of the circulator, when the pump turns on, it's the full 20 psi or 46 feet of head differential goes around the loop, and now my suction pressure is 12. So I'm maintaining positive pressure on the suction side of my circulator. So this sort of illustrates why you need to put your expansion tank on the suction side of a circulator. It's the safest place to put it. What happens if you install a flow center residential location? Where do you put it then? Well, that's a little bit tougher because these circulators are push-pull. And this one's pushing through the system, this one's pulling through the system. The best place to put it is at the lowest pressure point in the system, which is typically on the return side of your ground loop, right? Usually here. If you say, no, I don't want to install it there because I'm doing a retrofit, or I don't want to install it there because I want to have some isolation between my three-way valves and my flow center and my ground loop, the second best place you could put it would be at the suction side of the circulator going back out to the loop, okay? So those are the two locations if you're installing in a traditional residential application with the flow center. But important, try to always put your expansion tank on the suction side of a circulator at the lowest pressure drop point in the system. Some other considerations you want to think about. A lot of times people don't use expansion tanks or stopped using expansion tanks historically because they would rust. They would condense, they get cold because the cold fluid, rust, leak, cause a leak point, and that's a problem. All you need to do is install some kind of a thermal break between the installation point of your expansion tank and the plumb-in point of the system. And you can do that in a whole host of ways, but definitely put some kind of a thermal break in between if you're using a steel expansion tank, put a thermal break in there so you don't have the expansion tank sweating and rusting and failing and causing additional problems. Always include an isolation valve so that you can shut off the tank for a couple of things. One, for service, but the other thing is for installation. And keep in mind, you can use 2 expansion tanks instead of 1. 2 small ones will have the acceptance volume of 1 larger one. And connect them at the same point. If you start connecting expansion tanks in different spots around the building, you're going to have to do a lot of work to figure out what those pressures are going to be throughout the building. And there are tees available, HDPE tees commercially available that allow you to fuse the tee into the piping, HDPE piping system, and have some metallic port that you can thread in an adapter to connect your expansion tank. Typically a good idea also to install your expansion tank with the discharge side of the tank up. So if there's any air inside the tank, it just kind of flows out into the system during startup. Okay, last thing, how do we start up a system with an expansion tank? Well, first, set your precharge, if applicable. If your tank, some tanks like this little one here, this is an HDPE tank. It does not have a Schrader valve on it to set a precharge. It's factory precharged at a fairly low level, which means basically is you're assuming that this thing has very little elevation head or water column on the plumb end point of that particular device. This guy's HDPE, so it won't sweat or cause issues with failure over time. So starting up, we're going to set our precharge. If you have a Schrader valve, you can set your precharge on it. Fill the system with the isolation valve open, so any air inside of it gets the buoyant force of the air will go into the piping system, so you can flush that air out. Then close your isolation valve, flush your system. So now I've got no air in my tank, I've got no air inside of my loop. Then you deadhead your flush cart like you always do to check for air in the system. If you do not have an isolation valve in here, when you deadhead your flush cart, it's going to force fluid into the tank, and the water level inside of your flush cart is going to drop, and it's going to look like there's air in the system. So if you need to account for that, either by having this isolation valve or understanding that when you deadhead your flush cart, there's going to be some fluid that gets pressed into your tank. If it's a very small tank, like a little 3/4 inch tank, there's going to be very little water that gets pushed into there, so it may not affect the water level drop in your flush cart by much, but please keep an eye on that. And then once that's done, you'll open up the isolation valve, you'll pressurize your system that charges the tank. So now I've got a tank full of fluid that has pressure on the air side, and that fluid's ready to be pushed back into the loop as the loop pressure falls. There's a lot of information there. I've taken up most of my time. If you've got questions, I'm always welcome to stick around longer than the presentation scheduled to answer those. Otherwise, I'll turn this back over to Jeff.
Thank you, Tom. Great presentation. And I guess our challenge for the weekend is to try to use viscoelastic in a sentence at this point. I don't see any questions in the chat. We'll give everybody just a couple of minutes. It's about 28 past the hour, so we have a little bit of time. If you would type in your question. Oh, there's a gentleman with his hand raised. Jacob, if you want to state your question.
Sure. Thanks for that, Thomas. That was great. One thing you mentioned, that obviously for a geosystem, we're trying to overcome low system pressure, which means that the expansion tank would be pushing pressure back into the system. But you said to set the pre-charge as low as possible. Wouldn't you want the tank to be at a higher pressure so that it has capacity to push into the system? I'm a little bit confused as to, wouldn't the tank just, if the system pressure dropped, wouldn't it just drop to zero?
So really, I can illustrate that best with this graph. So if you have a pre-charge on your system and you deadhead your flush cart to force fluid into the tank, the amount of fluid inside that tank is the amount of fluid that can be pushed back into the system during system operation, right? So we charge the tank with a flush cart to push fluid into it so that that fluid's available to be pushed back into the loop as the system pressure drops.
Right. Okay, so the pre-charge might be at 12, but you deadhead it to 50 or
correct.
So.
Yeah.
And okay, that makes sense.
So if you're at 12 and you deadhead to 50, well, in this particular 2-gallon tank, you've got 1.2 almost gallons of fluid to give back to the system. So as the system drops, as your loop pipe expands and relaxes from the stress relaxation, that fluid will go back into the loop all the way to the point where it reaches the pre-charge. So at the point of the pre-charge, it's not pushing any more water back in because there's no more water in the tank. So if you can make that pre-charge as low as you possibly can, it'll continue operating down basically to that pre-charge pressure.
Yeah, that makes sense. And so for a commercial tank, which are typically at 12, can you drop them to 0, or would you want to?
You would drop them to match the piping height above the installation point. So say you've got a 1-story building and all of the pipe is in the mechanical room, and you install the expansion tank, let's say on the floor, I don't know, just to make it easy. And your pipe goes, 1 foot up the wall. So that means you've got less than a half PSI on your tank. So that means you can drain the air out of that tank down to 1 PSI or basically to nothing. And then when you deadhead your flush cart, it's going to accept fluid starting at basically 0 PSI all the way up. So so yes, if it's in a commercial application, I would argue that you should reduce that precharge. You should reduce that precharge to the point that it equals the height of the water or the piping above it at the installation point.
Yeah, because we do a lot of like multi-story buildings.
Yep.
So let's say it's, I mean, there's a point where you would, but let's say it's 12 stories.
If your expansion, yeah, so if your expansion tank is in the basement or like 12 stories below and you've got a water column 12 stories high, you would probably have to increase your precharge, right? You're gonna have to increase your precharge at that point, because otherwise the fluid column is going to force water into the tank before you ever charge the system.
Right. Okay. Thank you.
Thank you, Jacob. We do have one question. I know we're about 2 minutes after. If you don't mind sticking around for this last question, Tom, that would be great. Kent asks, won't deadheading the pressure tank stress the bladder?
No, and that's the beauty of bladder tanks. So the bladder itself conforms to the inside shape of the tank. So as you're forcing fluid and the pressure increases on one side of the tank, I think this is a pretty good slide to show it. As you're forcing fluid into the tank, the pressure on the water side is equal to pressure on the air side, right? So the bladder itself is not really being stretched. It's just folding to conform to the inside of the tank. But it's not like it's not like you're stretching that tank, because the air side and the fluid side always have the same pressure.
Thank you, Tom. Do you have time for one more question? John has a question about non-pressurized systems.
Yeah, sure. I'm happy to. I'll stick around all day. I love this stuff.
What percentage of residential geosystems actually use an expansion tank, and how does a non-pressurized flow center affect this need?
So great question. I don't know that we have any data on how many residential applications use expansion tanks. I know there's a lot of contractors who have started using expansion tanks over the years. I know that at least one manufacturer includes expansion tanks in some of their heat pumps. So I would say that the number of expansion tanks in pressurized systems has grown over the years. It's probably much higher now than it was, say, 10 or 15 years ago when I first got into this business. So the number is actually growing because people have recognized that need to use an expansion tank in a ground loop system. Yeah, the presentation is focused on pressurized systems. Non-pressurized systems, an expansion tank wouldn't apply because you don't have static system pressure to concern yourself with. So on a non-pressurized system, the circulator gets its suction head with a column of water. And on a non-pressurized system, there should be, if properly designed, a cushion of air between the fluid and the top of the inside of the tank that feeds the suction side of the circulator. And that sort of airspace functions like a bladderless expansion tank or a compression tank. In those cases, if again properly sized and designed, you wouldn't concern yourself with an expansion tank.
Very good. Actually, here's another question. If you can stick around, David asks, is there an advantage to using a flow center versus a traditional inline pump?
I think so. The flow center is a package system that provides 2 3-way 4-position valves. Everything is foam insulated and put into a rigid cabinet that allows easy mounting, and they're pre-insulated in a factory to prevent condensation on the components. So they end up saving a lot of installation time because all the components that you need are there and they're all factory tested. So if you install just an inline circulator, and especially in an application that you're doing heating and cooling, it needs to be well insulated, and that's very, very difficult to do because of the geometry of the pump housing or the volute. And you still have to install three-way valves for purging or some purge points. Maybe that's an HDPE assembly. But when you add up the cost of all those components, what you find pretty quickly is that a flow center, a prepackaged system like a flow center is a pretty good deal. It's a pretty good value.
Thank you, Tom. I want to be respectful of everyone's time. If you need to drop off, feel free. But as long as we have questions, this is exciting stuff, at least for me anyway. I'll go ahead and read the questions. Dan asks a question here, or makes a statement first, I guess. I always set up my systems with a water makeup, double check valve, or double check backflow and a PRV to keep constant pressure and offset the seasonal pressure differential. If I install an expansion tank, what effect would I see? Or would this just be overkill or redundancy installing an expansion tank?
I think a couple of things to keep in mind. If you install a PRV and also are installing a makeup system, I think you have to be careful in makeup systems because they can dilute your antifreeze. So you have to be very careful to installing a makeup system that's just a water-based makeup system. If it's got antifreeze in the system, you don't want to do that because otherwise there's no way to monitoring. If you do have a system leak somewhere, you could dilute the antifreeze. You could be leaking antifreeze into your ground loop or somewhere in the building, etc. Let's say you do have a pressure makeup system, either freshwater or a glycol feed system. Do you still need an expansion tank? I think, again, overpressurization is not a great concern in geothermal systems. So I could argue that you wouldn't need an additional expansion tank. However, if you did install the expansion tank, it would give you further capacity. And also, in that case, you would probably help, you would install an expansion tank to help prevent overpressurization. So if you're including a PRV, you're probably worried about system overpressurization. If you're installing a makeup system, you're probably worried about underpressurization. And therefore, if you've got the PRV in the system and are concerned about that overpressurization, you can size an expansion tank in there to ensure yourself you're not going to see a super high system pressure.
Thank you, Tom. All right, next question from John. Any special considerations for closed loop concentrics like a Rygan, HPGX, or Twister, or GI4 from Geothermal Innovations?
I think the only special consideration that you would have to look at would be, is there, what's their coefficient of linear expansion on those? Are they going to expand and contract like the standard HDPE pipe? Are they going to expand and contract more closely to rigid piping like copper or steel? If you are using those types of systems, I would check with the manufacturer of the system, figure out what that thermal expansion coefficient is or what the expected range of expansion and contraction would be over the operating temperatures, and size your tank accordingly.
Okay. Thank you, Tom. I think that's all the questions we have. Great presentation. I appreciate everyone's attendance today. This is being recorded, so you'll see this on IGSHPA's website in the next couple of days. And, feel free to reach out if you have any questions. Appreciate everybody's time this morning. Have a great weekend and let us know how we can help. Thank you.
Thanks.